What unseen things will be revealed in this episode? Today we will uncover the secrets of computed tomography, CT. It's an advanced technology that everybody might recognize from hospital. There it helps to reveal the internal structures of organs like brain, lungs or joints. Is it all? Well, not really. The very same scans are also incredibly useful for industrial quality control. Professor Sasha Senck, a senior researcher at the University of Applied Sciences, Upper Austria. Welcome.
Hi.
And also my colleague Jiří Šesták from Advacam Sales Department. Welcome,
Hello.
Jiří.
Hello, everyone.
Welcome, guys. Sasha, my first question. Your background is very interesting because you have a PhD in biology, but now your research is connecting the biology and the real-world industrial computer tomography. What inspired you to do this blend?
I guess it was a natural evolution from metrology, which was part of my master's student thesis, to my PhD thesis, which concerns the reconstruction of, let's say, fossils in a wider sense, of skulls. And we scanned this very dense material using microcomputer tomography, because even with a medical CT scanner, and we'll go a bit into detail later, it's not optimal for scanning such high dense objects. And there's not so many fossils to reconstruct in the world, so we were searching for another application or other applications. And medical engineering was one application, for example, for reconstructing large defects in the skull. And those defects can be, let's say, digitized also with computer tomography, either medical or industrial. And then you can, based on the geometry of the skull, for example, create implants. And these implants can, for example, nowadays be easily generated, let's say, from polymers, from plastics with 3D printing, but also with additive manufacturing of metals. And if you have metals again, this is quite dense, so you need the industrial computer tomography. And this was a natural combination of methods, everything connected with imaging, because that's the greatest fun, let's say, we have.
How would you, by the way, introduce your field to someone who is absolutely tabula rasa, who have never heard about X-ray or non-destructive testing? What is it about?
Yeah, for the let's say the kids at the long night of research and so on, we introduce ourselves as material scientists. And material science is a broad field. I mean, if you're building bridges, you are an engineer, but you need some material scientists to decide which material you use. You better not use rubber or foam for a bridge. It should be halfway stable. And if you are dealing with material science, with different materials which have different properties, you need metrology. You can have a microscope. You just take a slide, then you cut it, and you take a look with the microscope. Or you take like ultrasonic testing. You can have ultrasonic testing also in the hospital. For example, if you hurt your knee, and then, or if you're pregnant, or not you, but somebody's pregnant,
you know.
Yeah.
Science
you
is
take
moving
ultrasonic scanning. And this is everything connected to material science, but the beauty of non-destructive testing is that you don't have to destroy the sample. You don't have to cut a piece out of, let's say, a bridge or a car if you want to have some images of a car. And one example, we as a physical object we take for this for the children who visit us at the university is like a chocolate egg or surprise egg. There's some plastic inside, and if you want to know what's inside, maybe your favorite figurine, without cutting the thing open, you take a CT scan.
Can you use it to fake the lottery?
Actually, I had this question a lot of times. I think it depends a bit also on the, how we say, the bong for the lottery. And there's more than the standard X-ray we are talking about. We here in Advacam for the very special detectors. There's some imaging modes besides the absorption. And I think, yeah, if this is the right bone you can see.
Okay. Very good business, Jiří, maybe for us.
But the CT scan is usually quite expensive, and if you win 10 euros, it's maybe not so profitable.
So we have to calculate it. Every magic comes with a price, Okay, you mentioned also already fossils, some medical samples. What do you consider the most unexpected or unusual sample you ever had in your hands?
For my personal experience, it was art objects and music instruments. So on the left side, you see a very famous in Austria, art object, which is from the Renaissance. It's a salt and pepper, how we say, device. It's made from pure gold, and it was hand-driven from single pieces, and this thing was stolen, I think even 2 times in Austria. And then it came back, and this art object came with the historians who take care about that from the National Art Museum in Vienna with security guys. And so because it's very expensive.
How long does it take to do such scannings?
The scan for this one, I didn't do it myself because the material gold itself is very dense, has a high C number. It takes quite long. So a standard scan, I would say, for an object of the size, let's say for a mouse from the computer, is like an hour or 1.5 hours for good quality. And for this one, because it was large, dense object, I would guess it was like 3 to 4 hours.
How would look like the device you are using for this? This is the standard tunnel for CT?
In this case, form follows function. So you have a medical CT on the left side with the gantry opening. It's like 80 centimeters in diameter. And you have like, it's not a couch, but a place to lie onto here. And the patient is laying here. Then you have this device. Here the patient is going through. You have 1 or 2 X-ray tubes here in this ring. And then you have a line detector in the outside with depends on the lines. And this one is machinery, one of mechanical engineering machinery, because it's a ton of moving mass, and it spins quite fast in a spiral mode. And in this time, the patient goes through the gantry, and this one is taking single X-ray projection images.
Yeah. It makes the slices, and then the picture is
from
reconstructed.
The single X-ray images, that's why it's called computed, because tomography is the slice, and computed tomography is because from the single X-rays you have the computation of those slices. And then the surgeon, for example, goes through the slices and says, okay, here's a broken bone, and so on.
Okay, let's stop here for a while, because I wonder what are the principal differences between usage of CT for human medicine and any other samples?
There's like a handful of differences. The main differences, and probably the most important one, on the left side of the medical CT, we're dealing with live objects. Yes. I would say the live objects is a bit too much with human beings.
If they are not dead already.
You can scan a mummy, for example. You have digital forensics, and this is also done. And X-ray radiation is harmful to the body. And since it is harmful, this radiation dose has to be minimized. And to minimize, this is let's say the major focus for in this case Siemens, but there's several producers, OEMs of those medical machines. It has to be fast and it has to be safe. The harm done by an X-ray or like a CT scan cannot be larger than the benefit from the actual scanning. Sure. So it takes like a second or 2 seconds if it's fast. Maybe it's just a foot. I was laying once inside here for a research project. Was a scan of my foot in high resolution, and it took less than a minute. So it was very fast.
But it means that these pictures cannot be as rich or quality as these pictures.
Exactly. So what is the use of the medical CT? You want to see, for example, a tumor, or you want to see if there's a broken bone, or if the bone healed, for example. On the left side, you see part of a foot bone. It's like 4 centimeters in diameter. And this is the image quality and also the resolution. Resolution in terms of what is the size of features you can actually detect in the object. And in this case, for a good medical CT, it's 0.4 millimeter.
0.4.
Yeah. And so the scan is, let's say, a few seconds or a minute. And what we're doing with the industrial CT or the microcomputed tomography, same principle. You have X-rays, which are going through an object. On the other side is a detector. And the projection images is recorded according to the density, let's say, density distribution of the object. And we are much more flexible. We don't scan living things normally with the standard industrial CT and have a much higher resolution. The scan takes then a few minutes or an hour or 2 hours. But what you see here, for example, this is actually part of the foot bone, and this is the outer shell, and this is like a sponge from bone inside of this bone in this case, which is mineralized. It's calcium inside, and you have the contrast between, let's say, air or the material around and the actual material. So everything which is bright here and also here, this is the denser material. It's the same object. You see a distribution. Here is less and here is more, but here you have the single features inside.
Yeah.
That's the beauty.
That's obvious.
Of course, it's a trade-off between the quality of the picture and the time. But some industrial applications also want to be very fast. For example, in the automotive industry, you know.
Now it's moving on a conveyor belt, for example.
Moving usually is rather bad, because if you have an integration time, you take a photo, which is like 5 seconds, and you take your camera and you do this one, then it's not sharp. For the trade-off you mentioned for industrial applications is more or less exactly the thing. Also with RoboCT, where we have the user meeting tomorrow, you have to be fast. But if you are fast and it's large parts, then you have the trade-off, because it's rather low resolution and a bit more noisy. So you have image noise, which you see around here a bit.
You have any practical experience with in industry, like for example automotive, in your research?
Yes. We had a research project. I think it's was finalized 2 years ago, which was with an Austrian. It's not a car manufacturer, but it's like a part manufacturer, and they produced aluminium parts, part of a motor, not an electric motor, but a gasoline motor. And they had exactly this question: how can we scan this part in 1 minute? This is more or less, we produce 500 parts per day, and you have to have so many parts per minute, let's say. And then you had the robots loading and unloading the CT machine, and in the background machine learning to analyze this one.
Yeah.
Inline, at-line.
What kind of flaws were they looking for?
They were producing with a special aluminium fabrication method, which uses a sand core. And this, if the sand core is not completely removed, then it's stuck into the actual channels where the gasoline is running and so on. And also, if you have large air inclusions, let's say pores and so on, this is minimizing then the mechanical performance. This was the major two things.
Yeah. It's important to mention that you are not alone. You are leading a group of scientists at the University of Applied Sciences, Austria. These are your colleagues, I believe. What kind of projects do you have, generally speaking? It's quite broad, I saw.
It's broad. I'm not leading the research group. I'm a senior researcher, so the right hand of my boss, which is Mr. Kastner in the middle, who's also the vice president for research and development from the University of Applied Science. And we have, and that's the beauty of it, a large variety of different specialities. So we have several colleagues, more or less in the background, who are specialized in software engineering. This is again the computed part of the computed tomography. We have large data files, so it's several gigabytes. We have chemists in the background. We have physicists. I'm a biologist by education. We have 2 medical engineers. So yeah. And the research projects, more or less industrial, is into non-destructive testing, less than, let's say, health and biomedical engineering, because this is our strength in the research group.
And what's the process of acquiring an industrial, project? They, from the automotive, came to you, and they have a problem, an issue, and ask, can you develop a solution, or how it looks like?
This would be one side of it, and sometimes we have to tell them, okay, that's not possible, because if it's the size of a car and they want to see micro cracks in a few micrometer diameter, it's not working. Or they have very large objects with a lot of battery modules with a lot of material inside. This is companies coming to us with a problem, and we try to solve it. This is one part, but also we have a lot of ideas, and we go with our ideas to improve with new detectors, for example, or with new applications, approaches, and nowadays a lot with a combination of hardware and software side to the companies, and then we do research applications together to get the funding, third-party funding.
And the industrial customers, they rather use your know-how and knowledge and equipment for solving the problems, and they coming back, or they establish their own solution for their processes?
It's a good question. Let's say the very strong connections, they're coming back to us.
Okay.
Because they see what the benefit is, what we can deliver. If it's a straightforward problem, everybody can do it. If it's a difficult problem, not everybody can do it, and so they naturally have to come back. But we also had customers, let's say, or questions where nobody came back, because the data we sent them showed some features which were not really wanted, and we have to sign a lot of non-disclosure agreements also.
Ideally they come back, sometimes they don't.
You are in a real danger because you know a lot.
For the industry project, this is a big thing.
Yeah, I see.
Yeah.
Unseen Talks.
Welcome back to the Unseen Talk podcast, and we are talking with Sasha Senck and Jiří Šesták about CT. The improvements are constantly required, I guess, because we hear a lot about new materials, lightweight materials, composites, additive manufacturing. Are these new materials putting even more stress to develop new ways how to, inspect them?
Yeah, I would say it's like a tennis game. Somebody hits the ball to you and you cannot reach it. You have to think about ways and means to solve the questions. And that's also nice working in academia, but also nice working together with industry, because they have the actual questions. We have our research questions, and we're a bit in the ivory tower, and we go in very small circles. But if they come to us with a new question, for example, I told you already, with a large part, but they need a high resolution. This is part of the research project we have now to improve the resolution on the software side, optimize everything we can on the hardware side, best detectors, best source, and so on. And
Is AI a thing right now?
AI is a thing a long time, but we were laughing, or I was laughing, and I told you can use as much machine learning as you want to if you don't know how to scan, and if you don't know how a carbon fiber reinforced polymer part looks like with porosity inside, then you will not improve anything. You have fun doing it, but
You also mentioned the automotive industry application where they want to scan 500 parts per day. So then the evaluation is done manually, or there's an operator evaluating the results?
I think in this case I can disclose it because the system is existing, and I show tomorrow at the RoboCT meeting a picture from that one. They're using a Zeiss system, and they have Zeiss, no disclosure here, automatic defect detection. Okay. And they have a golden part, and based on that golden part they can decide, is this a defect or is this not a defect, with a range like 95% confidence interval.
Okay.
Yeah. What's for example? What's for example specific about composites in terms of quality control and DT?
The lightweight materials is a large part. Also for the university, we have a whole studies with composites and lightweight design. The biggest, let's say, difficulty inside of microCT is a low contrast between the materials involved in this lightweight components. Yeah. So you have carbon fiber, let's say, and a matrix from epoxy, and the difference in density density is quite low. It's part of the research, part of the master thesis we're doing now, to increase this contrast using staining agents. That's again where biology comes into play, because this comes actually from medical engineering, from biology. And then the let's say the size of the components involved. The single carbon fiber has a diameter of 7 micrometer. But if you have Airbus and Boeing and they want to inspect the whole plane, let's say, this is the compromise you were talking to also. This is like the size and image quality and how fast you can do it. It's a bit easier with glass fibers because the density is higher, but the same problems is same.
Yeah, we believe that the detectors from Advacam can solve the, as integrated in one of your machines, can solve the problems with the low contrast for the small samples, and using it with robotic arms by Radalytica, they can solve also the bigger one. So we believe that on the both sides we have the solution.
Yeah, that's actually my question, because your colleagues were involved in implementing Advacam's photon counting white PIX camera into industrial solution CT system. What did this experiment showed? Can it be useful in such cases such as light materials?
Yes, it can be. It is already useful because we saw that the contrast, what I already mentioned, between the matrix material, like epoxy resin, in which the fibers are implemented, the contrast is much higher, or can be much higher, and also the noise, or the electric noise is smaller. And if you have higher contrast and less noise with, let's say, the same amount of scan time or even less scan time, then this is what the industry will want to have, actually.
Yeah. We have mentioned that there is a fundamental difference because we are using photon counting. How do we understand photon counting compared to, traditional flat panels?
We have flat panels. If you have a scintillator detector, for example, you have the integrated, or it's integrating the energy over the range which you're using. And for dense objects, you have a high energy, so this is even more pronounced. And let's say one of the, and it depends if you use a cadmium telluride detector for single photon counting, or the silica detector, there's a high contrast even at the low energies. So if you have low atomic number with your materials, you have even higher contrast. And also depending on, this is also not available at the scintillators, you have different thresholds. And if you put the threshold at the right way, and medical CT is, let's say, again, ahead of us, because the medical CT single photon counting detector, this will be the gold standard. It is already the gold standard, but it will be the normality, let's say, in 10 years. And in this case, we scanned electronic parts. This is already an image from Advacam detector, which my colleague Jonathan Klins did. And we are on the right way. You already see the different materials. You see also pores here in the image. And what on our side for the research is, how can we improve image quality while maintaining the scan time, let's say at the constant level. It's readout, it's detector, it's the calibration which have to be improved. And automation is a large part for our research group, especially with the software engineers, because I can do it with like 20 steps, which I told earlier, from putting the sample into the hand, mounting it, scanning it, and so on. But we want to decrease this time. And this is the okay and not okay for the industry. Standardization, the verification, validation, but in this case, automation is very, very much needed.
Yeah, automation is definitely one of the topics for the industrial CT, but also last couple of years the AI for 3D reconstruction is the topic. There are innovations on the detector side, X-ray sources side, but AI is the biggest topic. Last 2-3 years.
As always in life, if you know what you're doing, this will help. Yeah. If you don't know what you're doing, then you can use as much machine learning as you want to. This will not be happening. But we have the ICT conference, which was this year in Antwerp, and for Jan Cyber's group, they're working since years and years with the reconstruction side, iterative machine learning let's say, based in hyphens, this one makes great progress. So it's the hardware side, but lately, let's say last 5 years, is also the software side, what you said with the reconstruction. Not only the reconstruction, because this is, let's say, part of the post-processing, but you have the segmentation, you have the classification involved, and this helps immensely if you know what you're doing.
Did I understand you correctly that the medical applications are further in implementing photon counting than the industry? It's weird because usually the industry is leading, or not?
I think it's a matter of money, because there is much more money in health system than for the development of new technologies. Because from my point of view, the health is not the so price sensitive area or So I think it's more investments, and of course people care, and people care more and more about the health. So I think it's money there. So it means the speeding up the development.
All right.
And medical CT was earlier than microCT, not by much. And one of the best examples for the single photon counting medical detectors is scanning of children. If you can reduce the dosage with the same or better resolution and less dosage, this is a selling argument directly.
Exactly.
Yeah. And do you see photon counting in the industry in 5-10 years, like standard?
I'm not sure if it's standard, because it's a diverse market, I would say, and we have forced CT systems in our lab, and we're building our own stuff with the help of the friends from Czech Republic, from the Academy of Science. It depends on the application. If you have a specific application where it helps, then yes. But the standard flat panel will have, also with robotic CT, for example, I think always its place.
Hello, this is Unseen Talks, Sasha Senck, Jiří Šesták. Welcome again. Generally speaking, what are the major challenges to be undergone before you can get or adapt a new CT technology to the industry? Is it about cost, complexity, or just lack of awareness?
It's a conservative market, and it's taking, for new companies who want to adapt a new approach, in our case for the non-destructive testing, time and the right people involved also. Because, for example, here what I show, the research project we are currently doing with Interreg Austria and Bavaria with our colleagues, that you can invest for a new CT, let's say, but if the benefit of having a new technology involved with a lot of expertise on the technician side, and it doesn't give you an immediately benefit from that one, we talked about okay or not okay and something in between, and then the question mark starts to rise. And the same will be the case with the single photon counting detectors, because some, let's say, industries are quite open to new applications, because in aerospace or even in medical engineering, the quality standards are so high, they have to fulfill them. Also, if you need to get the ISO standards and so on, the norms, and in others where there's a large production amount of parts which are rather cheap, then I think the conservatism is rather preventing the implication.
Yeah, I heard the answer. Yes, this is beautiful image. This is awesome, but we don't need it. We don't need such quality images. We could even see something, some flaws that we wanted to hide.
Yeah. If you do metrology and you need to control the thickness of a part, and you have 500 meters of steel in a minute, let's say, then this is not the case. You need two sensors. They cost 100 euros, and you have a setup which is 40 years old and works. They have a software, maybe Excel even, and they get the 1 or 2, and 1 is okay and 2 not.
An important trend is also the integration of robotics, not just for handling the samples, but actually for carrying the X-ray equipment to the object. What do you think about this concept of a mobile robotic CT?
Hopefully this will be the next big step, because a lot of restrictions. So let's say one restriction of microCT or CT is if the object is too large, you cannot even scan it. If it's just large, then the resolution is low. But if the object is unmovable, what do you do with that one? So if you have, for example, companies or Airbus, let's say, just as one example, who are building plane and plane parts, you bring the non-destructive testing equipment there. There's traditional chirography, ultrasonic testing, thermography, but they have, let's say, limitations because the beauty of CT or even laminography, what I'm presenting tomorrow, is with the robot setup, you have 3D or pseudo 3D information. And if it's expensive parts, also let's say for rockets, SpaceX is using NDT also for quality control. This will hopefully gain the attention of the people who are in charge.
As you mentioned, you are one of the keynote speakers tomorrow at the RoboCT User Forum in Prague. Thank you for coming here.
Thank you.
And you will be presenting a talk, Non-Destructive Testing of Electronic Components Using Laminography and Microcomputer Tomography. Can you give us a sneak peek what it will be about?
The first sneak peek was already batteries I was showing you because, this battery scans is already a long time, years and years people are doing that, but there's new developments in battery chemistry, let's say, and manufacturing. So we are on the R&D side of delivering high quality images. The second thing where I brought a video with me is a special mode. This is the laminography mode, where in a robot you have on the one side the detector and on the second side the source, and then you can, let's say, move them into a plane or a wall, and then you get the pseudo 3D information which you see here.
You are like focusing in the different depths.
Exactly.
Here.
And what you see here on the video is always one focus plane is sharp. And in this case, it's a very planar object. So it's like a sheet of paper. Yeah. It's very thin, but very wide. Okay. And for microCT or for CT in general, doesn't matter if it's medical or microCT industrial, that's a very bad combination of features for this stuff. And in this case, you only have the X and Y, so not in the depth, but in the lateral dimension, but it's super sharp.
Do you see a room for photon counting detectors in the robotics CT area?
Yes, of course. This will be definitely the case. We were talking about carbon fiber reinforced polymers, which have low C materials involved. And you need for quality control, let's say, of 2 sheets of carbon fiber reinforced polymers with like a honeycomb structure inside, which is glued together and so on for quality control. And I saw very beautiful images from Radalytica and from Advacam already. You need high contrast. You need low noise. And this would be is a very good combination for non-destructive testing in this case.
Jiří, are there already any industrial customers or people who are interested in the robotic CT?
Yes, and the demand is increasing. So we talk to a lot of potential customers for the different type of applications, including the robots. And for the non-destructive testing or quality testing, we also see new opportunities in the conveyor belt testing. So it's using the TDI of our detectors. It's for the moving objects on the conveyor belt. This demand is increasing, but it's all linked to NDT of the larger objects or faster moving objects.
Yeah. Back to your speech tomorrow. You will be mentioning PCBs, as you mentioned, and especially 3 techniques: radiography, laminography, and microcomputer tomography. What are the strengths of these 3 methods? Can you compare them?
Strength for radiography, which would be just one image of a planar object, is that it's cheap and fast. Again, if it's working, if the system is not working, then you don't see anything because the focus plane which you see is not right. What you want to have, for example, is to get to defects, to pores inside of the solder joint of the solder paste. And this one is just a superimposed 2D image, but this one is plainly enough to get to what you want to have. Okay, not okay. 20% porosity is okay, 30% is not okay, and then that's that. But if you have, let's say, high-priced new GPUs or some, like we are showing tomorrow, prototypes, you need at least pseudo 3D information. And this is where laminography, what we just saw, comes into play, because we have throughout the whole object, which again looks like a sheet of paper or like a plate, the 3D information, and then you have the distribution in 3D of those objects also. And if you're talking about cracks or delamination, which can also occur in PCBs, which vastly decrease the performance or thermal or mechanical performance, this you cannot do with radiography. And CT for smaller, let's say, cutouts in very high resolution, if it's a special component, let's say.
Do you need also the material decomposition capabilities? In
If
PCBs.
you have it, we take it, that's for sure. If you can take a single photon counting detector, you choose your thresholds, and then you see what higher dense inclusions are, tungsten, for example, which are unwanted. And then you can go back to your process and see where those unwanted features come from. And that is a natural, also like a race. Do you have the technology? And then the industry will use it. If this is not there,
exactly what you are saying. It's the electronics or PCBs that are newly manufactured. So you do the quality check of a newly manufactured part, but you have also many things that are already out of order, and they are the rubbish. But there are many like items or metals that you can reuse. So you need the analysis of the material composition, and here we come with the Advacam detectors.
Okay, thank you both very much for coming here. Thank you, Jiří. Thank you, Sasha.
Thank you very much.
thanks for the invitation.
We are really glad that you have come here, and thank you also to you, listeners, for listening to the podcast till the very end. Stay calm and please stay tuned for the next success stories with a bite of Advacam inside.
Unseen Talks are brought to you by Advacam, a world-leading producer of single-photon imaging and particle tracking cameras. We're imaging the unseen.